expanders in there. I'm sure there's no doubt that instead of a ring, you should use an expander code.
How many people are we to check for?
About
How many are the nodes in your graph?
It's like the people in the school, something like 7, something like that. Yeah.
50.
It's going to be 60, about 60, between 55 and 60 people.
All right. So let me recall where we were yesterday, and I should say yesterday we did very good because I went through about half the lecture I wanted. So let's continue. Let's just continue to ask questions, and it's great if I don't get to cover the entire material. So yesterday we were describing LDPC code and a special type of LDPC code called expanders. So we describe LDPC with their Tanner graph. Which is a bipartite graph. Oops. So the graph has two sorts of, it has variable node and check nodes, and it's got edges. Okay, so a graph usually is a set of vertices and a set of edges, but this is a bipartite graph, so it has two types of vertices. One that we associate to variables, and the other one that we associate to a check. Okay, so these would be variables, and up here we would have our checks. And then we got edges. But edges are only between variables and checks, not between checks or between variables. Okay? So the other constraint was that this graph is sparse. So just to sort of help with your intuition, let's imagine that we had to program this. How would you generate a sparse graph, randomly? So let's say that we want the degree of the variables to be, let's call it delta V, to be, let's say 3. And let's say we want the degree of the check. Should the degree of the check should it be higher or lower than the degree of the variables?
What's the degree?
Oh, the number of edges coming in.
Okay.
Right? Should be higher. Why? Sorry? If you want, but yeah, okay, we want to expand from here to here. So you're saying here you should have a higher degree. Is that what you're saying? Okay, you got the right answer, but I'm not sure I understand why. So let's say, let's say 6 maybe or something. Okay? Let me tell you. So the reason, sorry, this is a delta. The reason they have to be higher is that the number of edge is what it is. So here you can say the number of edge, or I could just say the number of edges is equal to the number of variable times the degree of the variable, right? But it is also equal to the number of checks times the degree of the check. It's just two ways of counting the number of edges. Either you count them down here or you count them up here. It should be the same. So this tells you that the number of check divided by the number of variables should be equal to the degree of the variable divided by the degree of the check. And of course, you want to have more variables than you have checks. Otherwise, this would be an over-constrained code. Okay? So recall that if you consider number of variables minus the number of checks, this is equal to the number of encoded bits, right? So if you divide this by the number of variable, this is equal to the rate. Okay? So in some sense, the degree of the graph tell you the rate. So this would be a rate 1/2 code, right? It would encode, if you have 1,000 bits, it would allow you to transmit 500 bits. Okay, is that a good recap? All right, so how would you go about and construct this? So we just said that each one of those would have 3. And each one of those would have 6. And so on. So now, a good way to randomly connect those is to say, well, I'm going to label those 1, 2, 3, 4, 5, 6, 7, 8, and so on. And here, I'm going to pick a random permutation pi. And this is going to be pi of 1 all the way to pi of 6, pi of 7, all the way to pi of 12. So permutation, you see, it just shuffles the integers. And then you just connect 1 with 1, 2 with 2, 3 with 3. And you got yourself a regular LDPC code. Okay? That's how you would program this. The only thing that may go wrong with this is that you may have 2 edges linking. This is very unlikely, but it could occur. It won't occur on very large system, but it could occur. You know, when I program this, what I do in this case, I'm going to exchange this one with a random guy. Okay, I'm just gonna take this edge and that edge and just swap them. Okay, so you could literally use this construction if you want to program any of this. You just put your ports. You make sure that there's the same number of ports up here as there are down here, and then you randomly connect them. Yes?
You use the adjective regular. Does that just mean the degree is the same?
The degree is the same everywhere.
Right, but there's nothing regular about the...
Correct. It's these are regular graphs in the sense that the degree is regular, but otherwise it's random. Yeah. Okay. So we also talked about expansion. So expansion means I pick a set here. We said delta gamma expansion. So I pick a set S, and that will be a set of variables. And I look at, and I also want the set to be less than a certain fraction. This condition cannot hold for the entire thing. So up to a certain size, if I look at the neighborhood of this set, so the stuff that is connected to the set, well, it is larger than some fraction of the set itself. Okay, so it's expanding. Okay. This is a number, a positive number. We'd like it to be large. We want to construct these guys with a large gamma.
Has to be bigger than 1?
No, later on I'll be saying, for this thing to work, I need gamma to be at least this large. So for most application, I need gamma to be, yes, much bigger than 1.
But if it's less than 1, it's still an expander?
You could say so. Let me tell you why it would nonetheless be kind of non-trivial. Take a 2D lattice. If you take some bulk region and you look at the neighborhood, it's a 1D structure. So here it's not bigger than any fraction, right? It's like a power. So this is kind of a, right? If you're in 2D and you say, what's the neighborhood of this region? Well, it's only this. So this thing here scales, like, let's call this R. So you have your region is proportional to R squared, while the boundary is proportional to R. So the boundary is not a fraction of the bulk. Okay? But on these expanders, the boundary is a fraction of the bulk. That's the beauty. Yes?
I'm confused. This shouldn't hold for bipartite graphs, right? Like the surface code. Because you have the area as well.
Okay, no, so it's not that it's bipartite, it's that it's 2D. These graphs...
You're saying that the neighborhood is only the around this
Yeah,
surface.
yeah.
Well, actually, you have all the stabilizer inside.
Correct, correct. Yeah. Yeah, you could say you have all the stabilizers inside as well. I'll get to something else very soon. Well, right now, that's about the unique neighbor. But yeah, I just wanted to show that having like the neighborhood of a region being as large as the region is not something that you would expect in 2D. Yeah. Okay, so let me just try to build a little bit of intuition. Okay, so the reason this is good is because let's suppose that S here denotes the location of errors. So you have a random error, and S is the support of that error. So it's the union of all the bits, all the variables that have been flipped. Well, the syndrome of that error will be contained within the neighborhood. Okay? So this tells you that the syndrome of the error should be large. Okay? But that's not quite right because there can be some overcounting here. Because if, let's say that let's say that these are the two, this is the location of the error, and let's say that the graph locally looks like this. I'm going to erase this. Maybe the graph looks like this. So you would say, here's the neighborhood. This is where the syndrome is. That's true, the syndrome lives in here, but not every check here has a syndrome, right? Because this one is canceled. Because this one sees two errors and it's only checking the parity. Okay? So what we want to define now is the unique neighborhood. Gamma plus of S, and it's the set of neighbors that have a unique neighbor in S. I'm not going to write any formula for this. It's like, well, here it's these two guys. Right? They are unique neighbors. So clearly, the syndrome. So we have for an error of support S, the syndrome let's call it S, obeys this. So you'll have the syndrome will be supported, will definitely be in the neighborhood, but also and this one is not strict either. Can anyone tell me why? It's not necessarily strict. Because you could have, some of them have 3 neighbors. And that would make it odd again. Okay? But this one will be good enough for us. And here's the thing. Here's something that I would like to show. If you have a good enough expansion parameter, the unique neighbor also expands. Okay? Is that so if you're expanding enough, then it sort of means that the syndrome of an error will also be larger than the error itself. Okay? So let me try to show this to you. So for this, we need to assume something about the expansion. Assume that your expansion parameter is larger than delta V. Delta V is the degree down here. Okay, so here we need some expansion. In this case here, it would be 1.5. Okay? If G is a gamma delta expander, then it is now I got to get this right, a 2 gamma minus delta V, delta unique expander. So I don't want to give you, I don't want to write many mathematical proofs, but I will prove this one because it's a very simple and elegant proof, and it sort of gives you the flavor of all the other proofs that I could write down. Okay, so so here's the picture we should have in mind. So here we have our variables, and here we have our check. We choose a set in here S, and then we will have this unique neighborhood, and the rest we'll just call T, and the two of them is the neighborhood. Sorry about that. Everyone clear with this picture? Okay, so you got a set of variables. You look at their neighboring check. You have the unique neighbors and the one that have 2 or 3 or more connections to that set. Okay? And what I want to show is that if this guy is large enough, then so is this one. And that's not very hard to prove. Let's show this. So, on the one hand, I have the following equality. Well, the thing I just wrote down here. So I got the size of the unique neighbor plus the size of this kind of multiple neighbor is equal to the size of the neighborhood. I mean, the sum is true about the sets themselves. And this, by assumption, is greater than gamma S.
That's the thing you want to prove.
Sorry. No, okay.
What is the thing you want to prove?
If the expansion is large enough, then it's also a unique expander. Unique expander will be extremely important because it tells us the syndrome of an error is at least this big, right? So you'll see how, a lot of things will follow from this unique expansion. Okay, so this is an inequality. Well, I mean, this is a definition, right? We've defined T as the complement, the difference between those two. So this is true, and this is by assumption. Okay, and the other thing we know is that let's see. I want to write the unique plus 2. Okay, this is less or equal to delta V S. All right, let's think about this. So here I'm sort of counting
Arjun, the sizes?
Sorry. Yes. Size. Yes. Okay. So what am I doing here? I'm counting the number of checks that I can possibly be connected to. So this is the checks that are connected by a single edge. Then these are connected by at least 2 edges. Okay, so this is why you have the 2 here. So this is less, so this is undercounting because some of them have 3 and some of them have 4 and so on. So this is less or equal to the size of the set multiplied by the total number of edge coming out of that set. So I'm just counting the number of edges from the top and the bottom, and I'm undercounting from the top. All right? All right, now what we want to do is we just want to take, I guess, this one minus 2 times this one. Okay, so we'll do plus minus 2 times this. And what do we get? If I can still do algebra, it gives us minus gamma plus of S. These guys cancel. Less or equal. This one has the plus sign, so it preserves the size, the sign of this inequality. Less or equal to, what will it be? Yeah, and this one has the minus, so it's all right. I flip this inequality, so now I get 2 gamma minus delta V. No, sorry, the other way around. Delta V minus 2 gamma S. So I guess I want to be turning this around now. So I'll multiply by minus 1, and I get gamma plus of S greater or equal to 2 gamma minus delta V S. And that was the claim. Okay? So if you're expanding enough, you're also uniquely expanding, and unique expansion, I repeat, is very important, because anything that's in the unique expansion set of an error will contain a syndrome. Okay? So we can already conclude something about the minimum distance of a code. Let's say I build a code by building one of these tanagraph, and it's a delta gamma expander. What's the minimum distance? So I'm gonna test some errors, and I need the smallest error that does not have a syndrome. Right? Huh? Related to T? No. Let's say I take some error, S, and the support of that error is S. Okay? As long as this error has a unique neighbor, it doesn't even have to be big. As long as it has a unique neighbor, it can't be a code word. Code words don't have syndrome, right? So as long as it has so I take a small error, I find that it has a unique syndrome. I make it a little bigger, it always has a unique syndrome. When does this stop working? Yeah, it stops working when I go past delta n. Okay? So the minimum distance of a delta gamma, I erased, but a delta gamma. Remember, delta is this parameter that says, when does it stop expanding? For a large enough set, like, remember, if I consider this set of all variables, the neighborhood can't possibly be bigger because there are fewer checks. Okay? So at some point, it stops expanding. And remember that it typically stops expanding when so locally the graph, if you build this graph, and I could say this is your homework if you like to program, locally you plot this graph, you pick a node at random, and you plot its neighbors and the neighbors of its neighbors, and for a very long time it will look like a tree. At some point you will start looping around, but this occurs when you've almost reached the entire graph. Okay? And this is where things stop expanding, when you start looping around, because you don't have as many neighbors as you would on a binary tree. Okay? So this is kind of the meaning of this delta parameter. It's when does it stop expanding, and the minimum distance. So we have a theorem, minimum distance of a code obtained from a gamma delta expander is at least delta n. It's pretty cool. So there were a lot of questions about this yesterday, because we motivated a lot of this formalism by saying we'd like to correct a single error. Here we have codes that can correct a fraction of error. Okay? So recall that if the probability of error per bit is epsilon less or equal, I should make it less than what? Huh? Yeah, the minus one, let's make it strictly less. Okay? Yeah, you don't want to be exactly there. So if the probability of error per bit is less than this, then on average, you expect, or I shouldn't use on average, because it would be very bad if the thing only worked on average. You typically you get less than delta n over 2 errors. So you can correct them. You can correct them, and I should write in principle. Because it means that with typical errors, the code word you started with will be the closest to the bit string you receive. But you still need to find that code word, okay? It's some kind of optimization problem in some exponentially large space. So in principle, can be done if you have an infinite amount of computational power. But in practice, I still need to tell you how you would go about and find that code word.
So it would like typically again in like provide is like a central neuron segment.
That's right.
More large numbers.
Here I'm just invoking, things like, if the probability of error per bit is delta over 2, if n is very large, it's very unlikely that you get much more than bit. So, we could, I had a,
So typically always means in the limit of large.
that's correct, yes. And you want to maybe be comfortable below delta over 2, so you might want to subtract a small number, make sure nothing crazy happens, yeah. So it's not it's just the regular square root of n, right? 1 over square root of n.
No, but it's Gaussian.
It's a Gaussian, yes. Yeah, that's, yes. So,
That's very important.
no, that's indeed. So if I say epsilon is delta over 2, but then I subtract alpha, a small quantity, then it's the probability that I exceed this is exponential in alpha m, right? Yeah, so this is very, very robust. Okay, so we started with just the assumption that the graph is expanding. I haven't told you how to build and expand the code, but I can tell you that, there are recipe, if you want a certain expansion parameter gamma, you just need to choose delta V and delta C in such and such way, and then you're very likely to get an expander. Okay, so we got very good random construction. And then you could just literally program this. It takes like a few lines of codes, and you got yourself a state-of-the-art error correcting code. You can start your cell phone company. But you still need to figure out how to decode them. So this is the next thing we need. Okay, how do we decode these codes? Are there any other questions? So the logic here was that if you choose the parameters right, it will be an expander. If it expands strongly enough, it also uniquely expands. And if it uniquely expands, then we got ourselves a distance. Because any error that's less than this critical size will have a syndrome, because it has a unique neighborhood, a non-empty unique neighborhood. Yes?
So this theorem doesn't see the gamma plays any role. Like, so what is the advantage of having a higher gamma?
It does. I erased it. But if gamma was small, this could be 0. I don't know who asked the question, but okay.
So that theorem is valid if gamma is bigger than delta V over 2.
Yeah, that's right.
Okay.
Otherwise, this is just not true.
I see. But is it better if it's even bigger, or I guess?
Well, not as far as any of this is concerned. Because here we just wanted a distance. Now we'll be doing other stuff. We'll start decoding, and I'll have more and more stringent constraint on gamma. And yeah. Okay. So now I want to describe a decoding algorithm. And maybe I want to take a few minutes. This was not in my notes, but I want to stress the importance of decoding algorithm. So we heard about Steve yesterday told us about the repetition code. So this is a code where you just copy, x goes to xxx. And that takes an error rate epsilon to epsilon squared. Okay? And if epsilon squared is not good enough for you, you concatenate. So you repeat the repetition code. So, okay? So now that's your repetition code. I'm going to view this as a repetition code, a repetition code, a repetition code, and then 3 separate repetition codes. Let's say that these locations suffer an error. So when you decode this, you're going to say, oh, it was x plus 1. You're going to flip it, right? This one, does everyone understand this? Because now the majority is wrong. The majority here is wrong as well, while the majority here is good. So now you're going to take the majority of these majorities, and you're going to have an error, right? This is one decoding strategy. However, another way to think about this is that this is a 9-bit repetition code, and I flipped 4 locations. If I took the majority down here, I'd be good, right? Here the majority is x. These are 2 decoding algorithms for the same code, okay? 2 decoding strategies. So you see that the decoding is important, okay? And this is why I said the kind of common theme is in modern coding theory is to think of a decoding algorithm and work your way backwards to a code, okay? And the flip algorithm is a good instance of that. You just say, I'm going to come up with, well, I haven't described it, but like what is possibly the simplest decoding algorithm you can imagine, and then work my way backwards, and I figure out, oh, if the code is an expander, it works, okay? So this is how it's going to work.
By the way, for those who understand the U.S. Electoral College system, this is how we got President Trump. It's gerrymandering.
Yeah. Interesting. Yeah, so this is not just theory, eh?
Still wrong.
Okay. So let me describe the flip algorithm. Okay. So flip algorithm. And by the way, I'm doing a pretty poor job with references, but there are some in the notes. Yeah. Okay, so here we're going to assume it needs a stronger expansion. It needs gamma greater or equal to 3 delta V over 4. Okay, so the flip algorithm, I'm going to prove that it works under this assumption, which is larger than what I needed to get some distance, right? I need a stronger expansion. All right, so here's the flip algorithm. Okay, find, so you receive, starts with a code word. You receive a bit string that is the code word with some errors on it. So it has some syndrome. And then you do the following. Oh yeah, we'll say, sorry, just a little bit of, we'll say, that a check C is sat if the bits or the variables connected to it add to an even number. And we'll say it's unsat otherwise. If it's 1 mod 2. So in other words, it's unsat if it contains a syndrome bit, and it's sat if the syndrome bit is 0. Okay? So here's the algorithm. Find a bit. So algorithm. Find a variable with more unsat neighbors than sat neighbors. And flip it. Step 1. Step 2, repeat. Okay? So you just go over your variables. If you find one that had its more unsat neighbors than sat neighbor, you would think that it's likely that it contains an error. So you flip it. And you just continue until two things happen. Everything is satisfied, so you're back in a code word and keep your fingers crossed that it's the right one. Or every bit has more sat neighbors than unsat neighbor, and then the algorithm gets stuck. Okay? So that's a decoding algorithm. Simple enough, right? You could implement this.
If you mean you just read 1 and 5.
Yeah, so you just go over all your variables. You find one. This one has more unsat than sat. You flip that one. And then you start over. Of course, you update what is sat and not sat, right? Because by flipping this one, you've changed you've changed the parity of all the checks that are connected to it. So this is why you don't want to do this in parallel, because you could flip 2 that were connected to the same guy. So you do it one by one. Okay? So you could do it like if they're not neighbor, it wouldn't change anything, right? But yeah,
Does it matter what your find a variable strategy is, or it's just like any good one?
No, yeah, you go, start with number 1 and just go, or use something random. Okay, let's just establish a couple of facts about this algorithm. What's the runtime? How long does it take? Huh? N is certainly an upper bound.
Yeah, because you have to go over all the things at least once.
Oh yeah, sorry, no. I mean, how many of this step do you use? So, let me tell you a couple of facts.
They were saying if you had to add the values of the variables or the number.
Oh, sorry, I explained this very poorly. All I'm saying is a node is unsat if it's the check is not satisfied. So if you have a node up here, this would be unsat because this is not an even number. Okay, so a code word should add up to 0 mod 2 for every check. So a check that is unsat is one that it has a syndrome bit 1. Okay, so the runtime of flip is less or equal. I'm going to say number of checks, and it is also, so I don't want to say that this is less than that, I'm not sure. So let's call it t. The runtime t of flip is bounded by this, but it's also bounded by delta v okay. So these are two very simple bounds. So yeah, I assume that the code is subject to an error of weight NE. So NE of its bits are flip. And I have two independent bounds on the duration of the flip algorithm. One is it's less than the number of checks. Let me tell you why. And both of those follow from a very simple observation. The number of unsatisfied checks decreases monotonically by this algorithm, because you always flip a bit that has more unsat than sat. So after each step, you have more sat than, I mean, you've increased the number of sat. So the number of unsatisfied check keeps going down, so it can't run for more than the number of checks, right? This is like if you started with all checks bad, and you would remove exactly one at every step, which is not even possible. So it's like very loose upper bound. This one is slightly better. Can anyone see this one? NE is the size of the error.
Are you restricting this number, this weight of the error below the distance?
No. Here, no. So it may work or not work. That's a separate question. But it will stop. Yes?
For each error, you can mess up that many other checks.
Yeah. So that's, again, this is the number of onsat. An upper bound on the number of onsat that you start with. Everyone sees this? Because every bit is connected to at most delta V checks.
Why isn't it like over 2? Because it has to have more unsat than sat, so that you can't ruin like half of them or more have to be.
You might be right. I'm satisfied with this bound. But let me just explain. I'm not sure that you were giving the same argument. All I'm doing here is I'm saying the number of unsat is a decreasing function of time. Okay? And that's an upper bound on the number of onsat. I don't see how you can put that divided by 2, but there might be a more sophisticated argument. I'm not sure.
This is the number of flips you might have to do.
So,
But you have to search and find.
no, I'm saying I'm counting how many times do you apply step 1? Search a bit, flip it.
Search bit is free.
Yeah.
Search.
Yeah. I'm just saying
That's free.
the number of iteration of this thing.
Not actually free.
No. Yeah.
Says you can't do it in parallel. So.
No, but okay, if we want to get into the details, it's not very expensive either. Because so you can go through the list at first, and then every bit has the number of sat on sat. And when you flip a bit, you only have to update a constant of those, right? And you could sort them all the time, so you just pick the one on top of your list. Okay, so it's not very expensive. And that's because it's a sparse code. If flipping one would kind of change everything, then it would be expensive, but this is not.
That's helpful. Thank you.
Other questions? Okay, so this is the runtime. Now I want to tell you that it actually works, meaning that, it might stop because it just doesn't find anything to flip. But that we wouldn't be satisfied with that. We want it to stop because it's reached the right code word. Okay? And this will be very helpful. Okay.
So out of these two conditions, the lower one has strings T stronger than. So the right hand side of the lower one is smaller than the right hand side of the upper one.
The right, sorry.
The lower one is a stricter bound.
Yeah, this one is stricter. Yeah. Well, no. It doesn't need to. Like if you had a very big error, this would be overcounting.
Correct. So should I take the minimum of it?
Yeah, you could take the minimum of the two. We're going to be using this one because we're going to consider relatively small errors that are, this is all we'll need. Okay? So, all right, here's a theorem. If the size of the error is less than delta n divided by delta v plus 1, flip succeeds. By succeed, I mean it returns the thing you sent. Okay, so now, you see, I'm not getting the full minimum distance. I'm getting a hit, and you might say we're supposed to be correcting delta n over 2, and now I'm correcting something smaller. but I'm using what you might call the simplest algorithm ever. Okay? So more sophisticated algorithm will get you more mileage, but you know, it's a very poor man's decoder, so it's already good that it corrects a fraction of error, a smaller fraction than you would like, but it's still a fraction of errors, which is pretty good. Okay, so let's try to prove this.
One more question.
Mm-hmm.
It seems like the order you flip these variables could lead you to a different order. Like, is that possible?
Yeah, if you get stuck, you could get stuck in different places. But if you reach a situation where everyone is sat, then you'll reach. It's unique, yeah. If the error was large, then you could reach the wrong one, right? Nothing prevents you from that. If it's larger than the minimum distance, for sure, but if it's larger than this bound, we're not going to promise anything either.
What happens at the equality?
Uh,
Is there a special case at the equality point?
I would have to go through the details of the proof to figure out what happens. In these things, you got the n here. So plus or minus 1, I never worry about this. No, but really, I mean, I could pay more attention and tells you what happened. But this is an integer. This is a real number, so or it's a rational. So okay, so what's the key step? The key thing is that yeah. The key thing is that the error during the algorithm. So you start with an error of size NE, and then the algorithm proceeds by flipping one bit at a time. But it will operate for less than this amount of time. So you can't, so during the process, you may increase the error actually, okay, but not beyond a certain bound. Okay, during decoding, the total error never exceed never exceed this size. Is that clear to everyone? It was of size NE to start with. You have flipped at most delta V NE bits. So it can never exceed this size. Everyone's good with that? So that's the absolutely worst case, like if you'd be flipping perfectly good bits all the time. That's all you did. Okay. What's next? All right. Suppose flip halts with some unsat. Okay, so we have some unsat, so we're stuck. So this means that at this point, because it's stuck, it means that every bit has more sat than unsat, yet we are stuck. Yet we are stuck, yes, by definition, but yet we still have some unsat. Okay, so let's just count this. Okay, so let S denote the support of the total error. So, I mean, it's at the end. So you had the error you started with, and then you flipped a bunch of bits. Now you have an error that's supported on S. Okay? So total error, it's the error that occurred during transmission plus the stuff you messed up during decoding. Okay. So now, I think I'll need this. So I'll leave it there. All right. So if we look, we said that this This was the unique expansion lemma that I told you about, right? If the thing is expanding, then it's also uniquely expanding. But now I'm going to use this, which was my assumption. If this doesn't work, flip doesn't work. So now this is greater or equal to delta V divided by 2 times S. Okay, so what is this telling me? It's telling me that the unique neighbor of my total remaining error, i.e. these guys are definitely on SAT, is larger than delta over 2S. So the average, so the total number of syndrome bit is at least the number of edges sticking out of that location divided by 2 times the size of the location, which means there must be at least one bit in there that has more than delta over 2. Right? Does everyone see this? So this is, so you have your variables down here. Okay? So and I'm counting the size of the unique neighbor. And what I'm saying is that this unique neighbor, okay, is larger than, if I take half of the edge coming out of every bit. If it's larger, it means that one of them must have more than one bit. More than half of their edges connected to the unique neighborhood. So then we can't be done, because this one has more onsat than sat. Does everyone ask question if this is unclear? Yes?
Yeah, so I think I missed the part of why does this flip, can it get stuck in an infinite loop that you are kind of taking the same loop?
It cannot be infinite because the number of unsat is decreasing. It can only decrease because every time I take a bit.
That's because of how you choose the bits.
Yeah, that's right. I only flip it if it has more onsat than sat, so it systematically decreases.
Yeah, but why cannot it then increase that kind of?
Because yeah, it never occurs, right? You never flip a bit if that's going to increase the number of sat. So every move you do decreases the number of onsat. So if we get stuck, it means that every bit has more sat than onsat. But I just proved that no, because here's the total error remaining at the end. If I look at its unique neighbor, it is more than delta over 2 times the size of the set. Therefore, there must be at least one variable in there that has more than delta over 2 of its edges connected to this unique neighborhood. So you should flip that one. You're not done. Yes?
Can you get stack things exactly half on each pattern?
Choose delta V odd. So yes, yeah, it's a good question. I mean, I should be maybe a little bit more careful with some inequality, whether they're strict or not. But if you choose it odd, you're good. Everyone gets the spirit of this proof? It's really just kind of counting the size of sets. And you see, I mean, of course, these proofs were made by backward engineering, right? You come up with the algorithm and you say, oh, look, it's going to work if this assumption is true. So, and then you just, go backwards and find the proper code, and the algorithm works for a proper code. What it means is that if the error is less than this, it can't get stuck. It could get stuck on larger errors. Yes.
Sorry. It seems like only these the unique only the unique ones seem to be important. If you see inside
yeah, that's right. That's right.
they're the only ones who are actually doing the work.
Yeah, that's true, but this is kind of a pessimistic assumption, right? Because you have these other guys. Of course, the neighbors that are connected to 2, they're not participating. The ones that are connected to 3 are useful. But I should say that on these random graphs, it's very rare that you have these. Well, no, sorry, I take that back. No, it's just very pessimistic. Okay? I want to talk a bit later about kind of more realistic thing. And, very importantly, these bounds, these conditions are not required in practice. you can go far beyond these things, and the thing still works. Okay? But this is what we can. There's always a gigantic gap between what we can prove and what actually works. This is why, like, rigorously, the threshold for fault-tolerant quantum computation is like 10 to the minus 5 or so, and in reality, it's much nicer. Okay. Yeah, there's another thing. I'm not going to prove any of this. How am I doing on time? Okay. Yeah. Okay. So I'm not going to prove because I want to move to quantum error correction. But there's another very nice proof about a very nice property of the flip algorithm, which is the following. Suppose now that you are in a different setting. You receive your bits. You measure the parity. So now you have your Tanner graph. And your bits down here. You've received these bits. And you have some edges. And you've computed the parities. You store them. And then a daemon comes and flips some of them. Let's say that your syndrome bits are unreliable. Now this might sound a bit weird because you should like keep them in a safe place. But for quantum computing, this will be a very natural assumption. Because when I start measuring the parity of a number of qubits, it's very likely that the measurement apparatus will just fail. Okay? So now suppose that you have some probability that the syndromes are not reliable. So now you're decoding, you're trying to correct errors, but you're using faulty information to do this. Well, flip still works. You need yet stronger expansion, okay? But if it's a good enough expander, the flip algorithm still works. Now, working is defined in a, you have to be careful about how you define working. It is not going to return you to the code space. It can't, because it doesn't know exactly where you are. It has unreliable information. What it can do is reduce the number of errors. So the right way to think about it is that if you had a continuous process where errors occur, you measure your syndrome, they're wrong, you error correct based on those. And you just keep on doing this. Even if you have incorrect syndrome, flip would maintain the number of errors under control. It would prevent it from growing. So one picture that you can have in mind is like, let's say that you repeat this like for hours and hours. So you do thousands of rounds of this. And at the very last minute, at the last iteration, you get perfect syndrome. It's going to return you to the code space. Okay? So flip keeps the number of errors under control, even in the presence of faulty syndrome. So it's a very powerful algorithm. Okay? So I'm not going to go over this, but this is like absolutely essential to get anything working in the quantum world, because in the quantum world, not only not only will your bits suffer errors, but your measurement apparatus will also suffer errors. So you need something that is robust. All right. So before finishing this section, I just want to say a few words about sort of real-world decoding algorithm. So no one would ever use the flip algorithm. Not in a real-world application. The flip algorithm is what we call a hard decoder. Hard because it just comes up with a sequence of hard decision. I am flipping this bit. Now I'm flipping this one. Now I'm flipping that one. There's another class of algorithm that, so it's an iterative process, which is just a sequence of hard decision. There's another class of algorithm which are still iterative procedures, but they are soft. So they're not saying flip this bit. It says you should probably flip this bit with some probability. And then based on that, it iterates. So let me try to give you a flavor of those. These are called belief propagation algorithm, or message passing algorithm, or if you're a physicist, Bethe free energy, or they have a lot of different names depending on where you come from. But really, it is kind of a mean field treatment of the decoding problem. So let's take some example. So I'm not going to go into, so in the notes I have like the algorithm with all the details, so you could just go ahead and program it. But here I just want to give you some kind of a flavor of how the algorithm works. So I'm going to draw a random graph. We're not very good at drawing random graphs, by the way. We always pick local checks. Anyway, it's good enough. Okay, so, let's say that, these two guys have an error. Okay? Of course, you don't know about this ahead of time, but that means this check's going to be bad. Is this one going to be bad? Yep. How about this one? Yep. Huh? Oh, yeah, you're right. Thank you. This one is bad, and the last one is okay. All right. So you will start the algorithm. Every bit will tell their check what they believe happened to them. So they don't know anything. So they'll say, I was flipped with probability P. Okay? So all these guys will say, I was flipped with probability P. So I don't know if I was flipped, but here's the likelihood. All right. This guy knows that that it was either no bit were flipped or two of them were flipped, right? Because it has the right parity. All of them were flipped with probability P. So then it's just going to say, all right, what's the probability that this one was flipped given what I've seen? So I'm not going to write any equation. You know how to do, Bayesian calculus. What you do, you just list all possible bit string with their probability. Well, let's go through the exercise. No flip, this flip, this, yeah, no, I just want to list everything. Sorry, what am I missing?
101, right?
Sorry, 1, 1. Yeah, okay. Okay, this one occurs with probability. Let's just keep the order. This is going to be order 1. This is going to be P squared, P squared, P squared, P cubed. These are not consistent with the observed syndrome. So you're left with either this, or this. So now you're going to say, what's the probability that the first bit was flipped? Well, it's going to be this plus this. Okay? So that's how Bayesian calculus works, right? You just eliminate what is not consistent with your evidence, and then you just marginalize. So now you're going to send something back, which is going to be like P squared. Here, on the other hand, you know that one of them was wrong. So it would be the opposite. All the ones that are marked out would remain, and all the ones that remain would be left aside. And then you would just compute the marginal on each one of them. And this one would actually be something, I'm not sure, but it would be something like 3p or something like that. Okay? It would increase the likelihood that it was flipped.
Shouldn't it be over the 1 if you exclude the constant case? Because you know that something is flipped. Something is order P or higher.
Sorry. You're right. It will be order 1/3. Because it could have been this one, or that one. Yes, correct. So now each of these, so you're going to do this for every check. And now every bit is going to receive a bunch of messages. And now they're just going to take the geometric mean of these messages and say, that's my new prior. And you iterate this procedure. Okay? That's the working of belief propagation algorithm. So what you get at the end are beliefs for every bit, which are just the product of all these incoming messages. And they should kind of polarize to either, nah, you're not flipped, or yeah, you're flipped. Okay? And, this is really the Bethe free energy. So if this thing converges, it gives you the Bethe free energy of the spin model. So this is just for those of you who know about statistical physics. There's a lot of very nice relation between these algorithms and standard methods that are used in statistical physics. Now, these kind of algorithms are used in practice, and they're also quite easy to code. I mean, you could program those, and they get you much better result than the flip algorithm. Okay, because you're not processing just like zeros and one. You're using soft information, and you're using some kind of self-consistency condition. These guys will kind of at the beginning, these beliefs will fluctuate like crazy, but at some point they will reach a steady state. And you know that it's kind of consistent with everything you've seen. Okay? So these, if you use a belief propagation like this, all the kind of criteria, you don't need an expander, you just need a sparse graph. You don't need any of the condition that I wrote, so it works as a heuristic much more generally. What is important, however, is that it is a sparse code. Why? Because imagine that you had a check that was connected to like 1 million guys. Okay? It's wrong. Okay? It's a bad check. All right. It doesn't learn anything, you know. It's you, or it could be you, or it could be you. It provides very, very, very little information. Okay? So this is why you want to keep a sparse code. Yes?
When you talk about this being kind of like a mean field theory,
Yes.
is that another way of saying that this algorithm is not going to tell me anything about probabilities of correlations between the errors?
Absolutely. Yeah. So this is a very good point. So, you know, the whole thing is just a Bayesian inference process. You have the list of all 2 to the n bit strings, and they all come with their probability. And some of them are ruled out based on the syndrome. And you should just say amongst those, which is the one with the largest probability. But you can't do this because you can't write down the list of 2 to the n probabilities. So what you do instead, you say, so you understand that this conditional probability, the probability of a bit string, of a bit flip pattern, I should say, condition on the syndrome, is a correlated probability. So what you're doing here, you're approximating this correlated probability by a product. Okay, so this is why it's a mean field, because you're replacing something like probability of an error given a syndrome, and the error here is really an element of f2 to the n. You're replacing this by something like product over j, p of ej condition on the syndrome, where these are now over individual bits. And this is kind of, you know, a way of getting a self-consistent solution to this approximation.
Can I use analogy? The mean field, it works better if there are many neighbors, so many links. What in this case would be an element?
Yeah, I think, so usually you need some critical spatial dimension for a mean field to work. These graphs, if you think about them, they live in infinite dimension. What is kind of, right, because remember, if you take a ball of a certain radius on one of these graphs, the volume grows exponentially with the radius. So in some sense, they're the ideal setting for a mean field to work.
Why isn't it not exact?
Well,
The
okay, no. Oh, it is exact on infinite volume. So what you can prove, this algorithm is exact on a tree.
Okay.
When it starts seeing loops, it's not exact. And this guy sees only very, very large loops.
So what do they, I mean, when do you start seeing loops?
So when the radius is roughly equal to the radius of the system, but remember, the radius of the system is logarithmic in n. Right? So here, if we take a certain radius, r, radius of, just so everyone is clear, what I mean by radius, I start at a point, I look at the neighbor, and then I look at the neighbors of the neighbor, and I just keep on growing. The volume here will be exponential in r. So it's not embedded in any finite dimensional space, because in a finite dimensional space, you would have r to the d. Okay? But on the other hand, if your total volume is n, then the radius is log of n. So this is the typical size of a loop, okay, in these random graphs. Okay? Yeah, so all I wanted to say, this is the modern thing. This is what is used, I guess, in cell phones. And very importantly, it is not trying to guess what was the most likely error pattern. It's trying to guess for every bit, was it flip or not. This is very important because this is not going to work in the quantum case. Okay, so I would call this, it is a local decoder because it decodes every bit. It doesn't try to make a global guess. Okay? Any questions about this? Because now I'm going to change topic. 15 minutes.
So here if you want to consider also faulty measurements, faulty stabilizer, you just multiply the probabilities by...
So let me show you a good way to model faulty measurements. If I just add to every check a bit, a hidden bit, right? So it doesn't, so it's like business as usual.
You can pass information to the
Yeah,
TDD.
it's just a hidden bit.
Color.
Yeah. So you can use existing algorithms for this. It doesn't change anything. Okay? But of course, this is not an expander anymore, right? Because these are special bits. Other questions? So, all right, let's do quantum. So I recall my goal is to, now I've explained LDPC and expanders, and I've shown you how wonderful they are in the classical setting. So now what I want to do in the remaining 15 minutes is explain just kind of the basic formalism for quantum error correction. And then in this afternoon, we'll pick up with explaining the surface code as a quantum repetition code. And then the last lecture will just say, let's use exactly the same recipe, but replace the repetition code by an LDPC, and we'll get a quantum LDPC code. Okay? All right, so now just quantum error correction. All right, so we'll have a quantum code. All right, so I'm going to assume a number of things. If you don't know these things, stop me and I'll step back a bit. All right, so we start. What we need is a set of what we call stabilizer generators, which are element of Pauli X, Y, Z, and identity raised to the n. And I could even throw in a phase here. You know, sorry. 1 minus 1, I minus I. But these phases are not going to play any role in what we're doing. All right, so everyone's good with the Pauli matrices. These are just n-fold tensor product of either x, y, z, or identity. And we start with, so we got n qubits, and we're going to pick n minus k stabilizer generators. Sj. And with those, well, we're going to assume independent. We're going to assume that they're independent under multiplication. So it means like S1 is not equal to S2 times S3, for instance. Assume independent under multiplication. They can't generate each other, yeah. Also, they commute with each other. Si, Sj equals 0. Okay, so they also form an abelian group, meaning you can multiply these guys together and you generate the larger group, and everything in this group commutes with everything else because the generators commute with each other. Okay? They generate an abelian stabilizer group. S. So this bracket is often used to say generated by. Okay? It's the group generated by these guys under multiplication. All right, what is a quantum code? I'll use a curly Q because apparently I'm not good at curly C's. No, I'll keep using curly C's. It is the set of state in my Hilbert space, my n-qubit Hilbert space, such that Sj psi is equal to psi for all j. Okay, so it is the set of states that are plus one eigenstate of the stabilizer generators. Okay, so by the way, if they are, I could have written, this would be equivalent, S psi equal psi for all S in, that would be the same. Because if they're plus one eigenstate of every generator, and I take two generators and I multiply them together, they're also a plus one eigenstate of that product. Okay? So it's important that the generators commute with each other because, as you know, you cannot have two operators that don't commute with each other cannot have a common eigenstate. Like X and P can't have a common eigenstate generically. But if they commute, then there exists a set of common eigenstate. And these define the code. All right. So the analogy with the classical case, I hope, is clear. Each of these stabilizer represents like one row in your parity check matrix. Each one of those is a constraint. And you have n minus k constraint. So you have the dimension of the code is equal 2 to the k. Okay? The way to think about it, you start with a Hilbert space of dimension 2 to the n. Each of these constraints cuts the Hilbert space in half. Okay? So it's exactly the same argument as I gave for the classical code. Every row of the parity check matrix imposed a constraint on the bit string, and that reduced the number of bit strings by a half. Now we're just cutting Hilbert space instead of bit strings. All right? So you end up with a Hilbert space or a code of dimension 2 to the k. So you're encoding k qubits. You're encoding k qubits in n qubits. So this should sort of sound familiar. It's just the way the constraints are imposed. We're not dealing with bit strings here. We're dealing with quantum states. So the way to extract information from an eigenstate is with an operator and looking at the eigenvalue of the operator. That's how we measure stuff in quantum mechanics, right? So if I were to send you a state and I promised that it was a code state, what you should be doing is measure the stabilizer generators, checking that you get outcome plus 1. If you do, then what I told you was true. And if you don't, then you know that the state was not in the code space. And this is precisely how we're going to detect errors. Okay. Any questions at this stage? Okay. So there is, well, yeah, let's go through a little bit of. So what will be the standard error correction procedure? We start with a state psi, and I transmit this, or just it might just be a memory over time. It gets corrupted. What you get is not psi, but e psi. Let's consider something simple now. Let's assume that this is also an element Let's assume that E is some Pauli matrix. All right, so maybe you apply some Pauli X to the first bit, Pauli Z to the third, and so on. Okay, so now I want to measure, and let's call this psi prime. So this is the state you receive, which may contain error. So now you want to measure Sj psi prime, and this by definition is Sj E psi. And here's the beauty. Pauli matrices can either commute or anti-commute, right? So this is going to be equal to either E Sj psi or minus E Sj psi. because when I swap two Pauli matrices, I either get a plus sign or a minus sign. But psi eats S, right? Psi was in the code space, so it absorbs the S. So we're back with E psi, which is equal to psi prime. Or we have minus E psi, which is minus psi prime. This is if E Sj equals Sj E, and this is else. Okay? So, what does this mean? When we receive psi prime and we measure one of the stabilizer generator, we either get the answer +1 or -1. These are the two. You see, the state is still an eigenstate. So you either receive you'll either observe the eigenvalue +1 or -1, and this in turn will tell you whether the error that occurred during transmission commutes or anti-commutes with the given stabilizer.
But you don't know if it's +1 after you measure the stabilizer. You don't know if there is an error or not.
Well, what you know is that if there was an error, it commuted with that stabilizer.
Product of the generators. So
Yep. So you want to pick good generators so they detect errors. So we'll call the collection of measurement outcome of stabilizer measurement outcome S, which is equal just to some bit string, right? I should say. So I mean, this is kind of being the problem of being halfway between physics and computer science. You know, physics like +1 and -1, and computer science like zeros and one. So I'm going to say if there was a trivial stabilizer, I'm going to call this a 0. And if it was a non-trivial a trivial syndrome, I'm going to call 0. A non-trivial syndrome, I'm going to call 1. Just to have a perfect analogy with what we did classically. Okay? So now the name of the game is to you start with some error model. You say, well, every qubit was maybe affected by X, Y, or Z with some small probability epsilon, and maybe independently on every qubit. Now you have your syndrome, so you know that whatever error occurred must have obeyed these commutation relations. So then you go through your list of all 4 to the n possible errors. You remove the ones that are not consistent with the syndrome, and cross your fingers and hope that one of the errors stands out, and you say it must have been that one. Okay? So error correction is choosing E that maximizes the probability of an error given the syndrome. So it's always a statistical inference problem. Error correction is always a statistical inference problem. So you need prior knowledge of what was the set of possibilities together with their probability. Okay? So this is an error model. It could be correlated. You just need a model. Here's what I think the probability was. Now I've measured a syndrome. That's going to rule out a bunch of things. And then you need to find what is the most likely error that is consistent with this syndrome. So far, everything is identical to what we talked about in the classical setting. Everyone's good? However, this is not the right definition. Okay? Why is that? And that's the last thing I want to tell you about, but it's going to be super important for LDPC codes. There is a problem that we call error degeneracy. Depending on the point of view, it is a bug or a feature. For LDPC, it's sort of a bug. Error degeneracy. consider two error. E and E prime equals E times S, and this guy is an element of my stabilizer. Okay? Suppose E occurs. Well, first of all, E and E prime have the same syndrome. Why? Why do they have the same syndrome? Because they differ by something that commutes with everything. Right? So remember, this is an abelian group. So if E prime commuted with a given syndrome, so will E, because they differ by something that commutes with everything. So multiplying by, so that sounds pretty bad, right? It means that you can't tell them apart. So that sounds like a bug, doesn't it? But now let's say that we start with state psi in the code, and we transmit it, and what we get is E psi. I see the syndrome. And I say, I think it was E prime. So let me correct. Remember, Pauli matrices square to themselves. So if I think a Pauli error occurred, I'm just going to apply it again. That's going to remove it. So I diagnose here, I diagnose E prime, and this is not a crazy diagnostic because it has the right syndrome. So I'm going to correct. Here I'm going to have my correction, E prime psi prime. This is my correction. All right, so I haven't corrected with the right error. I corrected with the wrong error. So the total error is E prime E psi, which is equal to, I didn't do it quite right, but it doesn't matter, E S E psi. And so up to a sign I can flip those, but this is a global sign. Okay, you see what I mean? These I can move around. I'll say which is proportional, and the proportionality can either be plus or minus 1. E squared, which is the identity, S psi, and this is psi. Okay, so up to a sign factor I get the right state, but we don't care about sign factors. So what is the moral here? So degeneracy seems like, a bug because you can't tell apart two errors that are related by a stabilizer, but you don't need to tell them apart because if you correct with either one of them, it does the right job. Okay? But what's the upshot of this is that choosing the error that maximizes probability was not the optimal solution. You should sum up the probability of all the errors that are related to each other by a stabilizer and pick the most, so these are cosets or equivalent set if you want. You should pick the most equivalent set of error, the most likely equivalent set of error rather than the most likely error itself. It sounds like a technical detail, but it will be crucial. Okay? So I'll start with that this afternoon. And maybe if there are quick questions, otherwise I guess we have to go to lunch. All right, see you later.